Is that we've lost the second camera, it just went off. Again, this is actually new. I've seen that one before. We're learning. We can already see the sample, so we've moved the sample in. You saw the procedure before. Try to move it in without doing anything, okay? And you move close to the local electrode. So if I go and zoom in here, you can see it's just right in front of the local electrode. You can also see that it's not a brand new local electrode, so it's got also already got a little bit of dirt on it. That doesn't actually interfere with the measurement at all. So don't change the electrode to a new one just because you see the camera and you already see a rough surface, which already gives you an idea that that's probably not going to work. Okay, so the good thing also is that that's something pretty easy to even check on the rough polishing stage. You know, you do your polishing, you pull your sample out, you look at it. If it's shiny, it's good. If it's not shiny, it's not good. Pretty simple. But here you can see pretty easily that it's actually okay. So let's just do some fine alignment. So the location of the sample in front of the local electrode is not really just given by. You might be compelled to think that you put the sample just where it would cross over from here to here, or sort of at the end of the cone. But the thing with that is that the hole is not always in the middle, and the local electrode is not always straight at the end. So there's quite a lot of variation in manufacturing. So sometimes the good point, measurement point will be here, some of it will be here, some of it will be here, and so on and so forth. So the easiest way of doing it is actually there is a marker. So you can have in laser mode you can have a marker, an alignment spot. And you just put this spot wherever your last, okay, that's obviously now not working as well. Anyway, you can put that spot to the location of a sample that you've put in and that you've run and that has actually been properly aligned. Then you just move any other sample to that spot, and when you change the local electrode, you just do the process all over again. So whenever you move the local electrode, you might be changing the electrode, or the other thing that might happen is that you just you get bad contact with the electrode. Sometimes you don't get the pulses through. Just pull it out, put it in again, and then you need to realign everything as well. Because it's not just where the electrode is, but everything has a little bit of play in a UHV system, so it will never quite end up at the same position. Anyway, so you search for a good spot. If you've got relatively robust samples, if you've got electropolished samples, they're usually robust enough to just search for a good spot, so you don't really need to line it all that well, as long as you're still at a relatively low evaporation voltage. So I think that's going to work okay. I don't know that because I can't see the second camera. So usually we would align it in both cameras, but it's in focus here, so it's at about the same focus as the local electrode. So I guess it's going to be kind of alright, I hope. Okay, so one thing we'll check is, of course, we've got a specimen in there, so that's all good. And the next thing, of course, is settings. So in voltage mode, you don't have that many settings. So the settings that you have are most important the detection rate. The specimen voltage always starts at 500 volts, but if you interrupt your measurement for some reason, it will you can just resume at the voltage that you stopped, okay? Or maybe you use the laser mode first because you don't know whether your sample works all that well, and then you switch back to voltage. You don't actually need to switch off the high tension, you just keep it at the high tension that it was before and switch on the pulse. Then there's something called the interface evaporation interface evaporation control, or IEC. the interface evaporation control does is it measures within a certain period of pulses. On the older systems, it was 10,000 pulses. On the 4,000 systems onwards, it's 10 pulses. It measures the average amount of atoms it gets per pulse. So if it suddenly gets a lot of atoms per pulse, it will just step the voltage down by a predefined value, usually 3%, 4%, 5%. The reason for that is why this was implemented is that if you have a multi-layer stack, you might have a low evaporation field layer, high evaporation field layer, and then you go to a low evaporation field layer. So as soon as you go out of the high evaporation field layer, the low evaporation field layer will just start to evaporate like crazy, and it will usually end your measurement because your sample will blow up. The interface evaporation control detects that and steps down the voltage fairly rapidly. This is not particularly helpful if you've got anything but that case. So usually for most samples, unless you've got a good reason, keep it switched off. Okay. The pulse rate. Of course, the pulse rate. Voltage atom clock tab. The pulse rate usually in voltage. You take the highest pulse rate you can get. It's really limited by what the pulsar can do. The only reason why you would change it is really if you have an experiment where you want to follow the experiment as it happens. For example, if you do a self-assembled monolayer of some sort of chemical on the surface, you might want to pulse very slowly because you might want to tweak things by hand. Other than that, the only reason is if you've got something very, very heavy in your sample. For example, you might be working on something containing uranium or any other really heavy element. Then your ion might arrive already at the next pulse, especially in reflectron-fitted systems, because there the flight path is very long. Okay, but other than that, on the superalloy, there's no reason to go down. The pulse fraction. Is also an important choice. I think you already remember from theory why we need a certain pulse fraction. So the reason why we have a pulse fraction at all is because high voltage pulses at a high pulse frequency can really only do a certain voltage. So the one in the lead can do 1,750 volts as a max. The one in the new systems, I think, can do 2.5 kV, but it's very limited. If you have a non-local electrode atom probe, you need higher voltages, so you might need to pulse much slower. Okay, and this is why we put a DC voltage on and a pulse voltage. What we would ideally want is actually just a pulse voltage. We don't actually want a DC voltage; it's just a technical necessity. Okay. But then the pulse fraction, the high voltage pulses need to be high enough to make sure that you don't evaporate any atoms at the standing voltage while still evaporating everything during the pulses. So carbon is usually pretty hard to evaporate. That's why you need to have at least, well, there was some old research done by the folks at Northwestern and some in Oxford. They both reached the same conclusion that in most metallic systems you need at least 17.5% pulse fraction in order to evaporate things like boron and carbon. That's why very often you will see 20%. 25% is sometimes even better if you've got a lot of high and low field species in there to cover everything. but for most systems, actually 20% is pretty okay. If you've got something that only contains metallic elements, you might get away with 15%. Or if you're just doing some fundamental work on pure aluminium, like Baptiste occasionally does, you can get away with 5%. Because there's only there's only aluminium in there, so who cares, what the other elements that potentially would be able to do. But this is where these choices come from. If you're not sure what pulse fraction you should use, probably start with a high pulse fraction and work your way down to the lower end. You will see when the concentration starts changing in your measurement results, okay? 20% for most steels and superalloys is actually a pretty good starting point. But this is a very, very important. So pulse fraction and temperature are probably the two most important settings that you have. The rest is just you can tell the atom probe to stop after a certain time, after a certain number of events, or at a certain specimen voltage. We will always make use of that thing here and set it to 8,750. No, something like that. Anyway, somewhere roughly below 9 kV. The reason for that is that if you have 20% pulse fraction, your pulsar can only do 1,750 volts. So if you go above a DC voltage of, what is it, 8,750? I don't know. Somewhere around there, effectively your pulsar will not be able to increase its pulsing voltage anymore, but you will increase the DC voltage. So your pulse fraction effectively goes down and down and down and down and down, okay? That's why we need to stop at 8,000 or 9 kV roughly, or 8.5 kV. Of course, if you've got a brand new atom probe that can do 2.5 kV pulsing, then you can go to a higher voltage. But on everything up to the 4,000 systems, that's the limit you have. The other reason why we usually limit experiments to that voltage is that the higher the bias voltage is, the more violent your specimen rupture will be. So if you've got a specimen rupture at 12, 13, 14 kV, it's very likely that it will take your local electrode into the grave with it, okay? And this would make your experiment a very expensive experiment. So even if you do laser, unless you've got a good reason, we limit it to 9 kV as well as what 10 kV really. So above 10 kV, it gets a little bit critical. So, and that's actually all there is to it. Next thing is just start the acquisition. And then we will switch over to the data visualization program. So now it's starting the acquisition. And 2 thumbs up. 2 thumbs up. So here you can see the voltage ramping up, and here you can see the detection rate. So right now we're just getting some stray atoms that are on the surface coming off, but at least the field is high enough to get some signal. If you have specimen is very blunt, you probably will only get some stray hits here. Of course, if you look at the mass spectrum, it's all pretty noisy, so it's all some weird atoms coming off, and now that was probably a little bit of oxide coming off. And I think we're a little bit to the right, and a little bit towards the bottom. But apart from that, it looks pretty okay. Most electropolished samples I do tend to start working with the superalloys at about 3 to 4 kV. Let's hope this one is not different. And here we would usually go a log scale. Use log scale. Another thing that sometimes makes a difference is how the specimen voltage is ramped up. There's a couple of different algorithms you can choose from, so that it runs rather slowly, or it runs a little bit faster. But mostly are very rarely find a compelling reason to change the algorithm that does that. So surely hope it's not just a nice looking sample, but also a nicely working sample. And usually you can see here the detection rate it slowly goes up before we start getting some good signal. This is actually still just surface contamination oxides coming off. If you see these spots here, that's probably a little bit of water coming off. Water tends to aggregate in little spots on the surface and then come off. It's not looking all too great. It will turn off when it reaches 8,750 volts, which might not be that far off. So if you look here, with about 7 kV. But yeah, it could be fractured, but actually pretty hard to know. How did I get the server now? This one. So this is actually no. Now we're on the. Okay. Now for some reason I switched over. So this is the actual PC that runs. Not this one, right? Because this is remote desktop connection. Go back to the LCC. And now I'm on the server again. Okay. The problem now is we're actually daisy remote connection in a remote. Yeah. Okay, so actually now remotely connected into a PC that's still remotely connected into a PC. So the two UIs that just overlap and we can't get from one to another.
Maybe you can drag and drop the status bar. The other ones here.
I'm proficient in PCs. This is actually the reason why I think all measurement instruments should run Mac OS, okay? Then I would know what to do. No. Okay. I have a little putting in a micro tipper. Okay, this is okay. Usually, if you look at a lecture sample, you can usually tell if it's a good sample or a bad sample. You can't see the tip physically because it's you can usually gauge whether it's a good or a bad atom probe tip, and that one I would actually expect to give us results. So I might just give it a try if we can move it in and out. So this gets of course, this camera has a relatively long working distance and hence field of view. You have to believe me that all of this worked really nicely when we tried it out.
Is it not possible to create a second camera? Is it not possible to find the second camera? Or
So the thing with the second camera is actually it's a laser targeting camera. So it's on a piezo microstage because it needs to be aimed with of course, a couple hundred nanometers precision because the spot is only 2 microns. So you can't move it by hand. So there are coarse alignment screws, but there's fine alignment always has to be done in the computer, which is something that obviously didn't work out all that well. Well, the problem is it's aiming at the wrong spot. It's working, so the camera is working, but the camera is not aiming at the sample. It's aiming somewhere completely different, which means the entire laser system is aiming somewhere completely different.
take out the sample, try to move the electric and see if it gets in the field of the camera?
That would be a very. The question is, you never know where you're going to end up. So we probably would be sitting for hours just try to move our electrode to the camera.
Our machine would use moving in. It's not exactly in the camera field. Just move it just a bit
Until it's there. Yeah. The way to do when you do that.
But if you take the out of range,
Actually, that looks a little bit better. Okay, so we're going to try the brute force variant of just moving the sample left and right, and see if we can get any signal. But for that purpose, I should probably switch off the auto evaporation control, detection rate control. So now it just runs at 5 kb no matter what happens. So the other problem that we're dealing with is, of course, that we only can see one program at a time.
I think that's not the right axis.
Yeah, well, now it's obviously the wrong axis, so I need to go to the other one. But I guessed wrong which one's which.
you can shift this in the right click.
Right click here. Oh yeah. Right. But it's a line, that's a little bit hard. Okay, that's obviously these controls. Oh, so we're I think what we learn from that is it's really hard to experiment with just one of the cameras. I think that's really not. It's really not going to happen. So I think what we should do is actually move on to the commercial analysis software that comes with the Atom Pro to show you how to do some reconstructions and how to do the calibrations and what the different values mean in those. And resolve the issues until after lunchtime, and we might then try to do the leap experiments again after lunchtime. Because without the second camera, we just don't know where we are. The position, switch off the voltage. I need to click anything or anything. No. Yeah, so we will move back to the lecture theater and continue with the analysis bit, because I think this